first corner on the left-hand side. Comparing two means with equal variances. Don't get fooled by the fact that instead of using x1 and x2, they use the y1 and y2 here. It doesn't matter. And D0 is, we assume with the null hypothesis, the difference is 0, so that's just a 0 all the time also. That's just a kind of a placeholder. So really what we're looking at here is x1 minus x2 over the standard error. Well, gee, things got complicated real fast here. What's the standard error? The standard error is equal to, since we're saying that the variances are equal, I'm saying to myself, well, you know, if they're equal, they're never really perfectly equal, right? I mean, Levi had one example where he made up an example where they were absolutely equal, so you could just use either one. They're never really completely equal. So one might be 31.1, the other might be 30.9, right? Well, how do we resolve that? Well, we kind of take a weighted average of the two of them. We say to ourselves, you know, since I'm assuming that they're equal, why don't I pool all of these numbers into one group and say that instead of relying on my sample of 50 people for one standard deviation and 62 people for a different standard deviation, let's combine them all together so that we create a single standard error, which is an average, weighted average of the two of them. That's called a pooled standard deviation, okay? So that's what's happening here. First thing you do before you do anything else is you calculate a pooled standard deviation, right? And S squared, the variance is really what this is, right? S squared is equal to N1 minus 1, the sample size of the first group minus 1, times the standard deviation squared of the first group, plus the size of the second group minus 1, times the standard deviation of the second group, over sample size 1 plus sample size 2 minus 2. All of that gets calculated here, and then you take the square root of the whole thing, like we would normally, right? Take square root of the whole thing in order to get S. Remember, this is the S squared is equal to all of this. So S is equal to S pooled, the pooled standard deviation, is equal to the square root of this whole thing. Okay, so now you take that value, S pooled, and you put it over here on the bottom. S pooled, well, gee, now hang on a second. I have two different sample sizes. Remember that square root of n that I was going to use? Well, now, square root of n, the standard deviation divided by the square root of n is the same thing as saying the standard deviation times the square root of 1 over n, right? Because it's like just another way of expressing the fraction. You're factoring out the standard deviation, except now we have two different sample sizes, potentially. So what you do is S pool that you figured out from down here, you substitute it here, and then you multiply by the square root of 1 over the sample size, plus 1 over the sample size, take the square root of it, and now you have the standard error. You divide that into the difference between the two means, and you get your t-score. If that t-score exceeds whatever the t-score has to be for your particular sample size, I need to know what the degrees of freedom are, right? Okay, well, we're going to get to that in a second. Now, in order to say what the t-score I need to exceed is, my critical value of t, I need to use the sample size, okay, or degrees. I have to know what the degrees of freedom are, which is tied into the sample size. How do you calculate for equal variances the sample size? Well, you use this lovely formula down here. Degrees of freedom is equal to n minus 1 times n2 minus 1 over this, over 1 minus c, and c is calculated by this ugly stuff here. Now, would anyone in their right mind ever actually want to do this for degrees of freedom? No. Do you remember Levi said, you know, the sample size, it's equal variances. The sample size for this group is 150. The sample size for this group is 250. So rather than go through the pain and torture of calculating the real degrees of freedom, I'm just going to say the smaller sample size, the 150 minus 149 is the degrees of freedom. That's why he did that, because it's a very conservative approach. You know, if you pool it together, it's going to be bigger. Degrees of freedom going to be bigger than 149, which means it's going to be a smaller critical T, which is better for you, but he's willing to give that up so you don't have to calculate this.
Why does that work?
Excuse me?
Why does that work?
Well, because when you pool the two of them, you're looking at a bigger sample. In other words, when you kind of pool them, you're going to be looking at the combined 149, 150, and the combined 250 is you have a total sample of 400 people, right? So you could kind of weight them and get a number that's greater than 149, but you'd have to go through this calculation to determine what it actually is. So instead of doing that, you're going to take a number 149, which is below both of the sample sizes for either group. So it's it's well below what it's going to come out. If you really do this calculation, you're always going to get a number bigger than that, right? Because both samples are bigger than that when you start out. So we could go through this whole calculation and it'd be torture. In real life, when we are working with samples with equal variances, right? Number one, we would make that adjustment for degrees of freedom because we wouldn't bother calculating it. And number two, we would do this calculation. It's not impossible. We know every number in there when we take samples. It wouldn't be impossible to do this calculation if we're careful. But more often than not, you're not doing it by hand. You're doing it using software like SPSS. And we're going to do at least one sample by hand. And then we're going to work with SPSS and see what it looks like when you use SPSS to do each one of these different four calculations, with the exception maybe of the proportions. I don't want to confuse you on SPSS with the proportions, even though you can do it. Now, you remember the example that Levi used, the hooked on nicotine, right? The mean of the sample size of one group was 150. Sample size of the other was 182. The mean was 2.8. The for females, mean was 1.6. So we got sample size 1, mean 1, standard deviation 1. Sample size 2, mean 2, standard deviation 2. We have all the values that we need. Before I work on that, I'm just going to take a quick look at another set of formulas. What about if we assume unequal variances? That I don't want to assume that's equal variances and pool them. I'm going to assume that they're not equal to each other. What formulas do I use to solve for t then? T is always going to be the difference between the two means divided by the standard error. Thing is, you got to calculate that standard error again. So let's see what t is equal to. T is equal to x bar 1 minus x bar 2, mean 1 minus mean 2, same as always, divided by the standard error. Now, what's the standard error going to be equal to? Well, it's going to be equal to, look at this. We got another formula that's pretty complicated as well. Now, we have here everything we need to calculate these values. We calculate our s squared from our combined s square using this formula. We plug it in there. We have actually we don't even have to do that. We have s1 squared, which we know, s2 squared, which we know, n1, n2, n1n, n2, n1, n2, x1, x2. We can calculate our t value just the way we have it here, right? Just with this formula. Bit simpler. And my degrees of freedom are going to be when unequal variance, going to be n minus 1 plus n minus 2, n2 minus 1. We're going to add them together, subtract 2 basically, right, for each group. And that's going to be our degrees of freedom. This is a bit simpler than what we were doing before. So I'm actually going to save time, use this formula instead of using the assuming equal variances. We're going to look, when we look at SPSS, we're going to see that SPSS actually does both calculations, right? It calculates it for equal variances and it calculates it for unequal variances because it's a computer. I mean, it can, it's like, doesn't matter how difficult, and it actually calculates it uses this formula to calculate the exact degrees of freedom. And it never uses a z-score, no matter how big the sample is. It always uses the t-score, and it always have a t-score that's exactly right, even if it's 393. It doesn't have to look in between 400 and 300, right? So, because it has all those calculations built into it. So, if I were going to try and solve this problem, and I'm hoping I'm going to get it pretty much the way that Levi did it, I hope. Okay, let's go over here, notebook. Okay, here's my notebook back. Okay, so let's see if I can't do this now. Let's see. First thing I'm going to do is write down all my different values here. Okay. Okay, and guys online, just give me a minute. I'm going to take a quick look at see if anything's going on over there. N1 is 150, N2 is 182. Actually, I'll use F and M. F and M. Okay, X bar F is 2.8. X bar M is 1.6. S1 SF is 3.6, and SM, standard deviation for males, is 2.9. Okay, let me go back up here and look at this formula. Okay, let's see, that's the pooled standard deviation. Let's take a look at this and say, okay, my t-score is going to be equal to, now you can use this formula right here if the sample sizes are equal for both groups, right? But they're not equal for both groups in this case. So we have to go down here and use this formula. It's calling on my phone. I'm buzzing here. Oh, emergency alert, flash flood warning. Right. Okay, so at any rate, okay, so we're going to use this formula down here. Let me pull this up a little bit, see if I can't get it so we can see it a little bit better. So my t-score is going to be equal to, okay, it's going to be equal to, t is going to be equal to, it's going to be equal to x bar 1 minus x bar 2. 3.6 minus 2.5 is 1.1. That was easy. Over the square root of n minus 1 is 149 times s1 squared. Anybody want to square 36 for me? What's it come out to? 3.6. What's it come out to be? 10 point something? You guys have calculators there? S1 squared. In other words, 3.6 squared. What is it? I'm sorry, say it louder.
12.9.
12 point, I'm going to call it 13. Okay, plus N2 minus 1, which is 182, is going to be 181, right? Times S2 squared. S2 is 2.5. That's 6.25. I can do that one in my head. Okay, am I right? Okay, 6.25, right? Add those two together after I multiply them out. And that goes over, what does it go over? N1 plus N2 minus 2, which is 150, and 182 is 332.
It's 8 o'clock.
Which is 330, right? Okay, so all of this goes into one parentheses. And then we multiply that by 1 over 150 plus 1 over 182nd. Okay, so now we just go through the hard work of doing this calculation, hopefully without messing it up. Okay, so I'm going to, let's see, okay, so t is equal to 1.1, and I'm going to try and resolve this bottom part. Okay, first of all, 149 times 13. 1,000, how much?
937.
Okay, plus 181 times 6.25.
1,131.25.
Okay, good. Divided by 330. Okay, times, what's 1 over 1? What is 1 over 1/50th? 1 over 150 is a decimal place. 1 divided by 150. I want to get my calculator here too. Okay, 0.0, I'm going to call it 0.0067 plus 1 over 182.
0.0055.
Okay, good enough. All right, so now let's add this together. 1937 plus 1131 is 8, 6, 9, 29, 68. This is this then is 2968 divided by 300.
30?
I'm sorry, was it 330? 330, you're right, 330, right? Times, add these two together, and we get 55 and 67 is 0.01, see, 2, carry to 1, 11, 12, 0.0122, correct? Okay, and if we multiply that out, we get, let me get a calculator. Okay, I'm not looking at the guys online because they criticize me and keep telling me I'm wrong. 22,968 divided by 330 equals times 0.0122 equals, I get down here, I get the value 0.10, actually 0.11. It rounds out to, it's 0.0197. I get 0.11. So 0.11 into 1.1 is 10, a t-score of 10. Okay, anybody remember what Levi got? Did he get a large t-score? I don't recall, right? I wouldn't like swear by my calculations here because we ran through them quick, but you get the idea. Your basics, you just plugging in numbers at this stage, right? How many degrees of freedom do I want to lower? Now, I can tell right away at big t-score like that, I'm going to reject my null hypothesis, right? That's a ridiculously large t-score. So I think I made a mistake here somewhere. Something doesn't seem right to me. Right?
That's 6 times 2.5.
6 times, where is that? Oh, no, it's 181 times 6.25.
Oh, okay.
Right, it was 2.5. Was it 2.5 squared? Right, yeah, that's 6.25, right? Yeah. Okay, so anyway, well, we can go back later on. Just let's assume that I got it right for Pete's sake, just so that we can go back and go ahead. So my t-score is very large. I know already I'm probably going to reject it. But what is my critical value of t got to be here, right? Well, what is the critical value of t related to? It's related to the sample size. So if we're doing a problem that involves unequal standard deviations, how do we calculate the degrees of freedom? Well, it's n1 plus n2 minus 2. So our degrees of freedom are going to be equal to, what was the sum of them? 150 and 182. That was 330. Was it? Something's wrong there, right? 330. Where did my notebook pad go? Notebook page. Hang on. Note. Okay. What was that number? How that number? Oh, that was n1 plus n2 minus 2, I think it was. That's how we got to 330. So it's going to be 330. So if I go to my t table for 95% confidence, or alpha error equals 0.01, and I look up a t-score of 2, I look up the t critical that I need for a sample size of 330 or 229 degrees of freedom. It's going to be 1.9 something or 2 point something, right? T table. Everybody agree with me there? Any problems with that so far? Well, it's going to be like 100. So it's going to be like 1.98. 10 exceeds 1.98. So what do I do with my null hypothesis? I reject it because my p-value is bigger than my critical value. Something's right. I don't like that number. So something might have gone wrong there. I'm not sure that exactly what it is, but we can go back over it when we have more time and try and figure out what exactly went wrong. But you see that we have a series of equations here. I just want to go back to those formulas and let you know that you have one set of formulas for means when you want to calculate, assume equal variances in the two groups. You have another set of formulas for when you want to compare two means and assume they have unequal variances. And you have a third set of formulas for proportions. And what do we use for proportions? We don't use t, right? We use z. So z is equal to proportion 1 minus proportion 2 over the square root of P0 times 1 minus P0 times the square root of the two sample sizes. Well, what happened to this P0? What is this P0? P0 is a combination of the two proportions. It's an average of the two proportions. You're actually combining the two populations to get the average proportion and using that to calculate the standard error. Okay, that happens to be very similar to what you were doing before for standard error. You get your z-score by calculating this. And if your z-score, in this case, the z-score was 2.89869. And what is our critical value with z for 5% alpha? And since this is bigger than that, we reject our null hypothesis. Our main advantage here is that we can go to the z table, not the x table, the z table. The x table was Mulder and Scully, right? Let's see. Z table, Agresti. Here we go. Okay, we can go to our z table. Back here somewhere. Let's see if I can't get to this thing. Nope, I can't get to it that way. I used to be able, what do I have to do? Maybe that or that. There it is. That's how we do it. Okay, I think this is it here. Nope, that's enough. I have two T tables open. Z table. There it is. Okay, so what was it again? It was 2.864 or something like that. So 2.86. Okay. Yeah, this is not happening to them at home. This is local. Okay. So it's 2.86 would be the equivalent area below that on the distribution, on the normal distribution, would be 0.2%. If I'm doing a two-sided test, I double that, which gives me a p-value of 0.004. In other words, the fact that it was greater than 1.96 and I was working with the z-score means I can reject my null hypothesis at alpha equals 5%. But the p-value 0.04 for a two-sided test also tells me that I really have a lot of room there. I actually can reject it at an even lower level. You know, that the probability of being wrong if I reject my null hypothesis is not only less than 5%, it's actually more like 0.4%. Okay, that's one of the advantages of working with Z instead of the T table is you can actually, you know, like present that level of present the actual level of probability. Yes.
When you calculate T-score before, what did you do that with? In this example.
Oh, the example before, I think I came out with almost 10, right? Something like that.
T-score is almost 10.
T-score was almost 10. The critical C value was only like 1.98 because the sample size was so big. The degrees of freedom were so large. Okay, and I suspect that I might have done something wrong there because I didn't expect it to be cut that big. I don't remember Levi getting, for the same data, getting. Yeah, I would have to go back and look at it more carefully to see what I did wrong. You know, but it should come out roughly the same unless he assumed unequal variances. I assumed equal variances. I don't remember him doing a pooled standard deviation. He may have shortcutted it, like done it off screen and then used it here. You know, so I don't remember him actually doing. I was semi-paying attention at that point. But at any rate, hopefully you were paying more attention to me. In fact, that's quite likely since he used this shortcut for the degrees of freedom. He probably did a version using equal variances, right? And somehow or other, he must have already calculated outside of the lecture the pooled standard deviation rather than go through the formula here. Okay, so at any rate, but you guys get the idea, right? I mean, this is really just plugging in numbers to formulas, right? You have to understand what you're doing, you know, so you choose the right set of formulas, equal variance, you make that judgment and so on and so forth. but this is really basically what you're doing. So now I'm going to show you how we're going to do this with SPSS. So you guys at home awake? Because I haven't seen anybody add a comment here in the last like hour or so. Okay, good. Somebody's awake. All right, so I'm going to get this stuff out of the way, and I'm going to use close. I'll save it. What the hell? Okay, and I'm going to go over here. I have some data files to work with. I'm going to open up one of the bigger data files. Well, let's see. Let's open up. I'm going to open up test scores for starters. I think I remember what that one is, but I'm not positive. I was going to use NC birth data to start off with. When I open up the data in SPSS, SPSS works with the raw data. Did you guys notice that with these formulas, we use the summary data? The mean of group 1, the mean of group 2, standard deviation of group 1, standard deviation of group 2. You can kind of get away with that with SPSS, but SPSS is really designed to work with your raw data, organize and calculate these things for your raw data. But what do I mean by that? Well, let's take a look behind me. I'm looking at this data set where I see a whole bunch of high school athletes. I see their gender. I see a pre-test, a post-test. You know, they took some sort of qualifying test. There was some sort of intervention or something like that, so on and so forth. And I see, let's see, classroom number. I see number of students. I see a whole bunch of other stuff. Well, one of the things that I see is a pre-test and a post-test, right? Pre-test and a post-test. Gee, let's see if there's a difference between the mean pre-test score and the mean post-test score. Now, each student took a pre-test and a post-test. What kind of test is this? It's a paired samples, right? So I'm going to go up to Analyze, Compare Means. I'm always going to be working in Compare Means now. And I'm going to go, notice there's a one sample t-test, right? I'll get to that. Compare Means, I'm going to go to not the independent samples t-test, but paired samples. Sometimes you'll see that as dependent rather than independent. I'm going to go to paired samples. I'm going to say, okay, I want to compare the pre-test score to the post-test score. And I move those into, that's a pair of variables that I'm going to compare to one another. So I'm going to click in the options and make sure it says 95% into confidence, right? So I'm doing my test at alpha of 0.05. I'm going to click OK and see what my result is. My output window opens up, and it tells me the mean pre-test score was 54.96. The mean post-test score was 67. The standard deviation was 13.56 on the pre-test. It was 13.98 on the post-test. And the standard errors was calculated for each individual group, but we're going to use it. SPSS is going to really kind of combine them in a second. Okay, so now let's take a look at what we have here. It did a t-test for us. It said, okay, the mean of this group was 54.96. The mean of this group was that. So I'm going to say x bar 1 minus x bar 2, 54.56 minus 67.10. That's a negative number, right? You get a difference. You get that difference, and now you're going to divide by the combined standard error, right? Well, if I go down here to this bottom box, it tells me that the mean, the difference in the means was indeed minus 12, right? And the standard error that it's using, and it calculates that the same way you would have with your formulas, is 0.094, and it calculates not only a confidence interval, but a t-score. What's the t-score? It's 129, right? So we know we're going to reject the null hypothesis. In fact, the difference is so great that the probability of being wrong is less than 0.1%, right? My significance, SPSS calls my p-value significance, and it always does a two-tailed test. Okay, did just one line there, did all of these calculations. Notice my confidence interval is minus 12 to minus 11. It excludes that important number 0, so I know that the difference between these two scores is statistically reliable, be different than no difference between the two scores. Okay, our null hypothesis would have been the difference is equal to 0. Our alternative is that the difference is not equal to 0, and we checked on null hypothesis. Okay, so now I'm going to open up a different group. A different. Let me see what else I got here in the way of data. Okay, I'm holding off on that last one purposely. Test scores, high school athletes, coronary artery disease. Okay. This is also paired samples. I just did that, so I'm not going to do that again. No, I'm going to open up the big data set. No, I don't want to do that. Okay. NC birth data is 800 randomly samples births in North Carolina, and we have all sorts of mother's age. We have the sex of the child. We have a marital status, and so on and so forth. Well, I want to compare something that has two groups. Let's see if we know if the mother drank or if she didn't drink. And let me just go in here and see. I'm gonna say in the view, I'm gonna say value labels. I'm gonna turn off those. I can see that drink or not drink is a 1 or a 0, right? I could actually go to the variable view and actually look that up, drink or not drink. Well, 1, 0, she did not consume alcohol. 1, she did consume alcohol. Okay, so I'm going to say to myself, I want to compare the mean birth weight for babies born to mothers that drank alcohol during pregnancy versus mothers that didn't drink alcohol during pregnancy, right? So what am I comparing? I'm comparing two means, right? Mean versus mean, not a proportion. It's not a paired sample, right? Because they're all different mothers, right? We're not measuring the same mother twice. During this pregnancy she drank, and during this pregnancy she didn't. It's not the same mothers, different mothers, so it's independent samples. So I'm going to go up to Analyze. I'm going to click on Compare Means. This time I'm going to go to Independent Samples t-tests. Okay, so the variable I'm interested in is the weight of the child. That's what I'm finding the mean of. I'm going to do it in ounces. So we have it both ways. And the grouping variable, what I'm going to break those two up into, is going to be the whether the mother drank or not. Okay, and the mother, let's see, where is she here? It's, weight gain, smoke, drank alcohol during pregnancy. Okay, I'm going to put it in there. Notice it wants me to define the groups. That means it wants to know what are the two groups? What are the symbols for the two groups? Well, it was 0 and 1. Why is it asking me to do that? Because, for instance, if I had told it compare means by ethnicity, right? Well, under ethnicity, I might have 7 categories, right? Hispanic, white, black, Asian, Pacific Islander, and so on and so forth. So I might have a lot of choices there, okay? And t-tests compare how many means at one time? Only 2, right? You can only compare 2 means, so you got to tell it which 2. You would think it would understand that if it's only 0s and 1, that it should know that it is, but it actually makes you tell you. There would have been no choice. If it were a little bit more sophisticated, it would have known that. Okay, we can only use SPSS for paired samples. No, you can actually do SPS. You can actually do paired samples pretty easily without that. You can use Excel or a calculator. I'll discuss that maybe in one of the reviews. So I'm going to click on OK, and it's going to do our calculation for us. Now, what does it do? It finds the mean weight for mothers that consumed alcohol during pregnancy, and the mean weight for mothers, birth weight for children of mothers who did consume alcohol during pregnancy, right? Now, we got a funny situation here. What's the problem here? The sample size for mothers who didn't consume alcohol is very, very small. So now all of a sudden we got a little bit of a problem here, don't we? Well, let's take a look at the analysis that SPSS did. It says that, well, first of all, notice that there's 2 lines. The top line says equal variance is assumed. The bottom line says equal variance is not assumed. It does both calculations. Remember those 2 pages of formulas? It does it both ways. And it does an exact calculation for the t-score and confidence interval. Well, which of these 2 lines should we use? Well, it helps us out by doing something called, in this first box of four, in this first area here with these four boxes, the Levine's test for inequality of variances. Okay, and it calculates something called the F score. And the F score has associated with it a significance or a p-value, a probability of being wrong. Well, now, should I start with equal variances being assumed or unequal variances being assumed when I look at that test? What do we always start out with if we don't know in statistics? What's our null hypothesis always equal? What does it always contain? It always contains an equal sign. So I'm going to start with the assumption that equal variances are, I'm going to assume equal variances. I'm going to say that the variances are equal unless the Levine's test tells me with a level of certainty better than 5% chance of being wrong that they're different, that I can reject the idea that they're equal and then use the bottom line instead of the top line. Okay, do I have a significance less than 0.05, a p-value less than 0.05? No, I don't. So I have no justification for saying they're different, so I stick with them being equal and I use the top line. Okay, so I go across the top line. The t-score is 0.682. The significance is 0.49. I have almost a 50% chance of being wrong if I reject the null hypothesis. That's not less than 0.05, so I fail to reject the null hypothesis. Is there a difference between mothers that drink alcohol and mothers that don't drink alcohol in terms of the baby's weight? Well, look, 116 points, 108. Sure looks like it, right? What's our problem here? The sample size on one end was so small. And that the sample size of both groups influences the standard error. So it had that effect on it. So we didn't have the outcome that we wanted on this one, but I used the Levine's test to decide whether to use the top line or the bottom line. And then I used my t-score for to determine whether or not I can reject the null hypothesis. SPSS conveniently saving you the trouble of looking up the critical value of t, conveniently calculates the exact p-value for you that you want to be less than 5%. Okay, now I'm going to try another one of these problems. Okay, this time I'm going to go to Analyze, Descriptive Statistics, Means rather. And I'm going to go to one sample t-test. That's the only one we haven't tried so far, one sample t-test. I'm going to click on that. I'm going to say, I'm going to look at the North Carolina weights of North Carolina births. I'm going to look at the age of the mother in years. Okay, and I'm going to say, I know in New York State that the age of the average age of mothers giving birth in hospitals in New York State is 27. I'm going to make a number up. So I'm comparing, remember this is our single sample test. I got one sample, which is the ages of the mothers in the North Carolina, and I'm comparing that to a known value, 27 for a different state. And I want to say, and what it's going to do, it's going to calculate a t-score. So I'm going to click OK, 27. I'm going to get rid of that 0. 27, I'm going to click OK. Now let's see what it comes up with. Well, it tells me, gee, the mean for the age, oh, look at that. I got pretty close, right? The age of the mothers in North Carolina averaged 26.92. That's pretty good. I didn't know what it was. That's a pretty good guess, right? And the standard deviation is standard error. And the t-score came out to be only 0.394. It's negative because the sample was smaller than the mean that I was comparing it to. And the significance is not low enough to reject the null hypothesis. I'm going to do it one more time, except this time I'm going to make that number 30. I'll make that number 23, maybe 24. Maybe women in New York State give birth much younger. Let's say, okay. And when I did it this time, I got a t-score of 13.5 and a significance that's very large. So that's my single sample t-test. I'm taking one sample, comparing it to a set number. Well, the only thing I left out so far was the p-value, if you had proportions. And proportions, you would normally just go ahead and use the formulas, and not that daunting. I would just use Excel in lieu of SPSS. There's ways to use SPSS for proportions also. But SPSS is easier to use when you have the actual data rather than just the mean is this and the proportion is this and so on and so forth. The standard deviation is this. Not that you can't use it that way, but it's really designed to be used with this actual data. Okay, now, any questions? Does this seem, I know that it's, your head's swimming now. You've seen 3 pages of formulas. You've seen stuff done on the computer. So I know your head is spinning a bit. But just the fact that you could see that in certain situations you apply this group of formulas, certain situations you apply this group of formulas, certain situations, proportions you apply this group of formulas, but you always do the same operation. You get your null hypothesis, your alternative hypothesis. You calculate your means, you calculate your standard deviations of your groups, okay, whether it's one group or 2 groups. You then look at your sample sizes. You then calculate how many standard deviations apart, standard errors apart, your 2 means or your mean and your number, how far, or your 2 proportions, you calculate how many standard deviations apart they are. In order to do that, you got to calculate a standard error. You have different ways to calculate the standard error depending on what kind of data it is and what kind of test you're doing. That eventually gives you either a z-score or a t-score. If it gives you a z-score, you go to the z-table and look up the probability of getting that big a z-score. If it's less than 0.05, you reject the null hypothesis. If you do a t-test because it's a small sample and you don't know the population standard deviation, well then you calculate your t-score, and if it's greater than the critical t-value, how do you get the critical t-value? You go to the table with the degrees of freedom, the sample size, and you look up what that number is, and you reject or accept the null hypothesis. I'm finishing up anyway now, so don't worry about if you have to leave or something like that. So, I mean, mechanically, you're doing the same thing, but it's just in specifics in different situations, you're approaching them a bit differently. It's not impossible though, right? Right? I mean, it's confusing.